Now for 10.5, number 15, we're going to see a two-tailed test, but what's more, we're going to see one with data. And I believe this is a problem we already did. Maybe I'm going crazy. With apple juice. No, I'm not crazy. That is the same problem we did before. Awesome. I love when something beautiful comes together. All right, let's see here. So I've got the data already in. I remember I opened up the data set and copied and pasted it in from the online data set, and I'm going to take, because I'm lazy, I'm going to take the old chi-square info and I'm going to copy and paste it in. It doesn't really matter which one I did. I happen to do the left-tailed test, but it shouldn't really make a big difference whichever one you do. I'm going to make that smaller so we can kind of see what we're doing here. All right, let's see here. The null hypothesis. All right, is assuming, oh, look at that, assumed sigma is 0.06. There we go, 0.06. Alpha is 0.05, great. N, well, N is however many there are in this set. So I'm going to count, highlight the data, enter, beautiful, 22. And notice my degrees of freedom automatically figured, because I did cell referencing, as 21. Now the standard deviation is S. That's equal to STDEV of all that data. Boom. Okay. And it actually already figured the variance, although if you wanted to figure it another way, you could do equals variance, VAR, of that data, and you should get the same number. Yep, and we do 0.00199. Okay, this number, S squared, makes this number. All right, now the critical value. Well, we actually have a problem here. We need two of them. So let me right-click, insert, well, highlight those two cells, right-click and insert, shift down or shift up, it doesn't really matter. Okay, and actually I'm going to click and drag here, so that way I get some of this. Okay, so we need two of them. We need 1 minus alpha over 2, and we need alpha over 2. Okay, delete that, because we have two critical values. Okay, now we got to find them. Okay, so the first one is 1 minus chi inverse, equals chi inverse, of 1 minus d1 over 2, right? It has to be over 2 because alpha has to be over 2. Let me go grab the picture for y. Hold on one second, I'll be right back. There it is. It's on page 562. See that? The low one is 1 minus alpha over 2. The high one is alpha over 2. So you have two of them. You got to find both. Okay, so I'm going to have to do chi inverse of 1 minus alpha, which was in cell D1, divided by 2, comma, degrees of freedom, but degrees of freedom is in cell, whoop, there it is, D6. Enter. Okay, now the other one, I need chi inverse again, but I need chi inverse of alpha, which is D2, divided by 2. And of course, if you put yours in different cells, it'll be whatever cell you put it in. But for me, it's cell D2, comma, D6 for my degrees of freedom. Enter. Right? D2, see, D2, there it is. All right, these are my two critical values. Now the test statistic is n minus 1, which is the degrees of freedom, so that's this guy right here, the blue box, n minus 1 times s squared, right, there's s, caret 2, divided by sigma squared, right there. All right, notice that this guy is not lower than him or higher than him, right? Oops, if you look at the picture, if this one's 10 and this one's 30, oops, whatever it was, 35, okay, so this one over here is 10.6, this one over here is 35, you're at 11, you're in the middle. That is not the rejection region. You are not rare enough to reject the null hypothesis. Therefore, you're not going to reject the null hypothesis. Right? So let me type that. Right? We do not reject H naught because the chi-square statistic is not in the rejection region, not in the critical region. That's what it's called. Critical region. Lower than the low value, higher than the high value.